Good morning, everyone. Welcome back to Math 098 Elementary Algebra. We are going to move into our next set of guided notes. So we are now in Unit 5, which means we are going to solve systems of linear equations. Before we actually started recording this live stream, in the live chat, I asked all of you to share an example of an equation in standard form and an equation in slope-intercept form. And you did exactly that. I have lots of examples that's going to help us move right into what we need to learn today. Again, at any point, if you have any questions, don't hesitate to ask. I would be more than happy to break something down in a different way. We are going to learn some interesting techniques to help us solve systems of equations. And then later on in this unit, we're actually going to get into word problems applying systems of equations. So we'll be working with two unknowns. Okay, let's take a look. Recall from Unit 4, give an example of a linear equation in standard form. So Doc, you started us off by saying, well, 4x plus 8y is equal to 10. That is an example of an equation in standard form, and that's perfect. Ryan, you gave us an example in slope-intercept form that was y is equal to negative 2x plus 4, which is fantastic. I wanted to make sure that we incorporated at least one negative somewhere in our setup, so this is perfect. A system of linear equations is defined as two or more, okay? So two or more linear equations involving the same set of variables. For example, a system of two equations in two variables would be x, y. A system of three equations in three variables would be x, y, z. Now, I actually inputted parentheses around the x and the y and the x, y, and z to show that the solution to a system of equations with two unknowns would be the ordered pair x, then y. If we had a system of three equations with three unknowns, it would be the ordered pair, or excuse me, the ordered triple, x, y, z. Ordered pair, ordered triple. Makes sense? So before we actually get into methods for solving, we need to know that there are three types of systems. The first type is called a consistent system. This one's actually great, and all it means is that your two lines intersect at a very specific point. So if I were to plot this point just to identify the intersection, that particular point where these two lines cross represents the solution of our system. Hopefully that makes sense. To solve for this system, they have to have a common point. In this case, they cross here, and whatever that value is. That could be, if every mark represented one whole unit, we could say this is a half, comma 2. That would totally work. So a half, comma 2 would work in this case. Imagine if we were counting up by twos instead. So maybe that would be 1, comma 4, right? So it just depends on the value of each of these. But for all, all intents and purposes, we're just going to say that this is 1/2, comma 2. Notice that I've written the solution as an ordered pair. This is actually really important. Your solution must be expressed as an ordered pair. If you just say that x is a half and y is equal to 2, recall what that actually looks like. X is equal to 1/2 is a vertical line, right, with undefined slope. If you have y is equal to 2, well, that's a horizontal line with slope of 0. But when we say, good morning, Ria, when we say that two lines cross at a specific point where the ordered pair is 1/2, comma 2, that is more meaningful. So I want us to be very careful when we write our solutions. We need to show that we recognize it's a point on a graph. Okay, make sure you write your answer as an ordered pair. Okay. Our next type of system of linear equations is something called an inconsistent system. Notice here that our two lines never intersect. We know what it looks like, and we know what kinds of lines we have when they never intersect, and that is parallel lines. When two lines are parallel, they have the exact same slope. What I've given you here are the equations of two lines. So if you have your notes handy, you can see that this first line has the equation 14x minus 4y is equal to negative 4.5. So the equation of this line is in standard form. The equation of my second line is y is equal to 3.5x plus 0.25. They look very different, but I want to prove something to you. What I'm actually going to do is, first off, I know the slope of my line here because I've expressed the equation in slope-intercept form. So if I made a quick note, I could say that m is 3.5 for this first line. What I'm going to do right now is I'm actually going to take the 14x minus 4y is equal to negative 4.5, and I'm actually going to solve for y to prove to you that they have the same slope. Now, because we have decimals, I'm totally comfortable leaving the rest of the work in decimals, so bear with me. We are first going to subtract 14x. Recall that when we want to write our equation in slope-intercept form, the goal is to get y by itself. Also recall that if I want to write this correctly in slope-intercept form, we want to make sure that we're writing the rest of the equation in descending order. I'm going to divide each term by negative 4, right? That's one of our rules learned from chapter 2. If you multiply or divide, you must do that to every single term in the equation. We bring down the y. When we take our calculators and punch in negative 14 divided by negative 4, you get a positive 3.5. So we get 3.5x, and then when we do negative 4.5 divided by negative 4, we get a positive 1.125. So notice that the slope for my second equation is also 3.5. So even though the equations looked very different, the graph shows, okay, that looks pretty parallel, but I can prove that. If I write the second equation in slope-intercept form, then I can say, yes, we were correct. They are, in fact, parallel because they have the same slope. So if this ever happens, there's no solution, okay? They do not cross anywhere, so there can't be a solution. Inconsistent system, no solution. Let's turn the page. Next, we have something called a dependent system. And this one's actually pretty interesting because it's not something that we really think about all that often. But if your two linear equations in your system are actually the same, meaning they're the same line, then there has to be an infinite number of solutions. Notice here how the two lines completely overlap. I tried to showcase this, that you have your line in the background and you have this line in the foreground, and they're completely on top of each other. So they intersect at an infinite number of points, right? So you would actually say infinite number of solutions as the answer to this particular system. Again, how we know this is because the two lines are actually the exact same equation. So notice the system that I have here. Y is equal to x plus 2, and then negative 3x plus 3y equals 6. At first glance, you're probably thinking, they don't look the same. Well, I'm going to take that second equation, negative 3x plus 3y is equal to 6, and I'm going to isolate y. I'm going to rewrite the equation so that we are looking at this in slope-intercept form. I have one last step of dividing each term by 3, and I get y is equal to x plus 2. Take a look. They're exactly the same, even though at first glance, they didn't look identical. Okay? So these are perfect examples that show you what these kinds of systems look like when you have the case of no solution or infinite number of solutions, and then, of course, one solution. So in addition to there being 3 types of linear equations, there are actually 3 methods for solving systems of equations that we cover in this class. Later on, if you pursue mathematics, you will recognize that you can use matrix algebra to actually help you solve systems of equations. It's incredibly fun. If you're ever interested, look that up, matrix algebra. It's super, super cool, but we don't cover that in this class. We only cover graphing, substitution, and elimination. So going back to the notes, we have to recall our methods for graphing. So the first one we can recall is graphing by plotting points. Hopefully you remember the process for graphing by plotting points. If you don't, that's okay. You can always look back to the previous videos or you could check your Unit 4 notes. But recall with graphing by plotting points, you rewrote the equation in slope-intercept form first. Then you strategically chose two values for x. You inputted them into the equation, you outputted their corresponding y, and then you had two ordered pairs, which you plotted on a graph, and you connected with a line. Simple as that. The second method we had was by graphing the x and y intercepts. Okay? As a reminder, the x-intercept is of the form whatever that x is, comma 0. And then the y-intercept is of the form 0 and then whatever that y value is. So as a reminder, we would plug in 0 for y in the equation and solve for x. That would give us our x-intercept. If we want the y-intercept, we start again. We say, okay, this time let's make x equal to 0 and then solve for y. Those 2 points you would graph and then connect with a line. The third method we learned was graphing by using the slope and y-intercept. So essentially, if you hear the phrase slope and y-intercept, you automatically know you're using y equals mx plus b, where m is the slope and b represents our y-intercept. So these are the three methods that we already learned from Unit 4. The second method is something called substitution, and the third method is called elimination. I will tell you right now that substitution and elimination can be used whenever you want, right? They're interchangeable. Sometimes there are equations that lend itself really nicely to substitution, and other times elimination is the way to go. So I show you all three methods, anticipating that you're going to choose methods 2 and 3, substitution and elimination, over graphing, especially when you're dealing with fractions or decimals. You want to have exact answers. So using substitution or elimination would be the way to go. Okay, and of course, unless you had graphing software, which we're trying to learn everything by hand, so you don't have graphing software, technically. Okay, you will find that these are interchangeable, so I want you all to really become experts and masters in both of these styles, so that way you could say, oh, this system, I should be using substitution, or for this particular system, let's definitely use elimination, and you'll be able to make that decision the more practice you actually take, okay? Let's take a look. First, we're going to check out how we solve systems by graphing. This should actually go pretty quickly because we've been graphing this whole time from Unit 4. So our first equation is y minus x is equal to -1. Well, what I'm going to do, and I hope you all agree, is we need to just rewrite this in slope-intercept form. So I'm going to add x to both sides. That leaves me with y is equal to positive x minus 1. There's my first equation. No worries, Kayla. Welcome. The next equation, we have y plus x is equal to 3. So again, I'm going to rewrite this in slope-intercept form. So we subtract x from both sides, and we get y is equal to negative x plus 3. Now, you should all be able to, at this point, tell me the slope of each line and tell me the y-intercept of each line. So what I'm going to do here is I'm going to write slope is equal to y-intercept, and I'm going to write it as an ordered pair. I want you to fill that information in for the first equation and for the second equation. So slope equals, and then the y-intercept. Go ahead and type that into the chat. Excellent work, Noelia. So for the first equation, Noelia recognizes that the coefficient of our x term is 1. If you don't see a value here, you know that it's a 1. So that means my slope, or the m, y equals mx plus b, is a positive 1. My y-intercept is our b term, so that's going to be 0, negative 1. Noelia went on to say that for our second equation, our slope is a negative 1, right? Y equals mx plus b, where the y-intercept is 0, 3. At this point, we are going to plot this information, and then, of course, we're going to connect with a straight line. So for our first line, one at a time, okay, start with your y-intercept of 0, negative 1. So 0, negative 1. And now we want to apply the slope, which is a positive 1. Remember, slope should be represented as a fraction. So because this is an integer, we can write it over 1. So it's rise 1, run 1. Rise 1, run 1. Let's do it again. Rise 1, run 1. And one more time. So we connect this with a straight edge. Let's go ahead and do that the best that we can. I want to make sure this is nice and as straight as possible. Ooh, see, always writing all over this card. Perfect. There's my first line. If it helps, we can label this first line as y minus x is equal to negative 1, just so that we remember which one we graphed first. This next one, we're going to start with the y-intercept of 0, 3. So 0, 1, 2, 3. Here's my starting point. And then my slope is negative 1. So as a reminder, let's place this integer over a 1. So we have negative 1 over 1, which implies fall 1, run 1. Remember, we never run backwards. So we're going to fall 1, run 1. Fall 1, run 1. Fall 1, run 1. And now let's connect with our straight edge. Excellent. We can label this line as y plus x is equal to 3. Notice that this system is consistent. Okay? This system is consistent because it has one point of intersection. There's one solution. And that solution is right there. So when we write our answer, we can say solution. And then we can recognize here that this point pertains to 2, 1. So the solution is 2, 1. Now, as a reminder, I want you all to be able to check your solution. So in this case, if you wanted to check it, all you'd actually have to do is plug in your values into the original equation. So let me show you what I mean. I'm going to take a scrap sheet of paper out. I'm always ripping my paper. That's okay. If the solution is in fact 2, 1, x, y, I should be able to plug that into both of my equations in the system and it should check out. Let me show you what I mean by check out. So we have y minus x is equal to negative 1 and we have y plus x is equal to 3. Remember, we are testing the ordered pair to 1. Recall every ordered pair is of the form x, then y. So what we're going to do is we're actually going to substitute the values. Y is 1, so we have 1 minus, and then x is 2. And we're going to check it out. 1 minus 2 is, in fact, a negative 1. So negative 1 equals negative 1? Yes, it does. That checks out. However, just because it checks out in one of the linear equations doesn't mean it always will check out in the second. So you need to test both of them. But by plugging this in, we can verify rather quickly that yes, the ordered pair 2, 1 is the solution to that system of equations. I hope that makes a lot of sense. X, Y, plug them in, check them out. If it checks, beautiful. You've done this correctly. Let's take a look at number 2. We have x minus 3 is equal to 4, and 2y minus 5 is equal to 1. So again, if I wrote each equation out separately, just so you could see what's going on, I would hope that your gut instinct here for the first equation would be to get x by itself. Maybe at first you freak out and you're thinking, whoa, there's no y. But then you remember that we have something called vertical and horizontal lines. So not having one of the variables is actually not a big deal. So x minus 3 is equal to 4 says to us, okay, let's add the 3. Let's isolate the variable, right? That's something that we've been practicing this whole time. So that gives us x is equal to 7. Okay, I'm going to hold off on that. The next equation, we have 2y minus 5 is equal to 1. So if you did take a step further, you would say, well, let me just add the 5. So we have 2y is equal to 6. And then you'd say, let me take it one step further and get y alone. So then you have y is equal to 3. Now, remember, we are graphing lines. So x equals 7 is a line. We just have to figure out and recall what that looks like. So one of the things that I recommend to my students is take that first step by identifying where x would be 7. If you had to just identify that first, you would probably say, well, this is my x-axis. So if I had to figure out where x is 7, I would go to 1, 2, 3, 4, 5, 6, 7, and I would plot this point. So then my next comment to you would be, well, what is that point? What is that ordered pair? And you would say, oh, that's 7, 0. So you would write 7, 0 as your first ordered pair. And then you'd think about this and say, well, I need another point to make a line. And x has to be 7. So if I wrote another ordered pair, x has to be 7. Which means y could be anything we want it to be. I'm going to leave this blank because I want you to put your own number here. Okay? It doesn't matter what that number is. There's no restriction. X has to be 7. That's the extent of it. So you can put any value you want here for y. Okay? X has to be 7. That's the rule. So having said that, I'm going to pick any other value. So I'm going to pick 7, 4. 1, 2, 3, 4. And then, because I have my 2 points, I'm going to connect them with a straight line, which you will do the same. Okay, there's my straight line. Draw arrows on both ends, and then I'm going to label this x minus 3 is equal to 4. I'm going to do the same thing with y equals 3. So again, if you go to the y-axis, where is y equal to 3? Well, if we went up 1, 2, 3 units and plotted, we would say, okay, y is definitely 3 here. And that ordered pair is 0, 3. So underneath, I'm going to write 0, 3. And then that's going to be a reminder to me that says, oh, I get it now. I get it now. Every time I write an ordered pair, y has to be 3 because it says y is 3, which means x could be any value I want it to be. So I'm going to leave this blank as well. I want you to put any number you want here and then plot that point. For me, I'm going to say that I want to plot the point -2, 3. So -2, 3 is right here. Then I'm going to connect with a straight edge. And then we'll see what's happening here. Draw arrows on both ends and then label this equation 2y minus 5 is equal to 1. I apologize, I went off the screen a little. Notice here that we also have a consistent system. We know it's consistent because there's one point of intersection, and that's right here. Do you see where these two lines intersect? So the solution in this case would be the intersection 7, 3. But doesn't that kind of make sense? If they tell you that x is 7 and y is 3, Okay, that's the solution. X is 7 and Y is 3. Cool, right? But you're able to see this graphically. And I want you all to be very confident with graphing vertical and horizontal lines, which is why I provided that example for you to do. Let's turn the page. Okay. Let's now talk about the substitution method. I'm going to walk you through this idea of substitution method, and then we're actually going to take a look at a couple examples. So when you have your system, the first thing you want to do is you want to isolate one of the variables. So let's take a look at our example. Negative 4x plus y is equal to 6, and negative 5x minus y is equal to 21. Now, if you look at the first equation, notice that it would be very easy to get y by itself. All we would have to do is add the 4x, right? If I took a look at the second equation, it would be fairly easy to get y by itself again, because I'd have to move the 5x and then I'd have to divide by a negative 1, right? So what I actually did for you all in showing you the steps for substitution method is I decided to isolate y in the first equation. So you can do anything you want. You can isolate any variable you want in your system. You just have to pick one equation and you have to pick one variable. But there's strategy behind it. You don't want to solve for something that's going to leave you with a ton of fractions, because that can get messy pretty quickly. You want to isolate a variable, if possible, that has a coefficient of 1 or negative 1, if possible. That's definitely not always the case. Far from it, right? But for the examples we're going to see, we need to look for the most helpful approach. So that's why I'm recommending for these particular two equations, getting y by itself is going to be the easiest task. So let me show you. So what I've done here is I've added the 4x, right? And I've isolated y. So y is 4x plus 6. By the way, if I wanted to, I could have taken negative 5x minus y is equal to 21, and I could have done the same thing, but this time get y alone in this equation, because that leaves me with negative y is equal to 5x plus 21. Then I divide each term by a negative 1, not a y. Y is what we're trying to get along. I divide by negative 1, the coefficient of my y. And that would leave me with y is equal to negative 5x minus 21. Okay, so that's actually an alternative to this. But keeping this aside, I'm going to leave this over here. I just wanted to show you that I can solve for y fairly easily in this equation as well. Let's go back to what we were given. So step number 1 is to isolate one of the variables. Cool, which I did. I'm saying here that y is 4x plus 6. Okay? I'm going to write this out. Y is 4x plus 6. So step number 2 says, take that expression, the 4x plus 6, and plug it into the other equation for that variable. So I'm saying y is 4x plus 6. So it's almost like you're revealing what y is. So in our second equation, the one that we did not manipulate, right, because we're only focusing on this one, we manipulated the first equation, which means I need to take that y in the second equation and replace it with 4x plus 6. This is like information, right? We use the first equation to inform us for the second. This is a system, so they must work together. You must take one piece of information and input into the other equation. So take a look at how we do this. We had negative 5x minus y is equal to 21, but we know that y is 4x plus 6. So check this out. Where I had a y in my equation, I replaced it with a 4x plus 6. Negative 5x minus y, but y is 4x plus 6, so I replaced y with 4x plus 6, is equal to 21. Do you see how these are exactly the same, with the only exception being that we substituted 4x plus 6 in place of y. Now that I did it, I just have to perform the indicated operations, right? So we have negative 5x minus parentheses 4x plus 6 is equal to 21. So we distribute the negative 1 to both terms. Negative times 4x is a negative 4x. Negative times 6 is a negative 6. So we have a negative 5x minus 4x minus 6 is equal to 21. At this point, we definitely have to combine like terms. So negative 5x and a negative 4x is negative 9x. Then we have negative 9x minus 6 is equal to 21. At this point, we add 6 to both sides, right? So as a reminder, you're trying to isolate the indicated variable. So we add 6 to both sides, which leaves me with negative 9x is equal to 27. At this point, we divide both sides by negative 9, and I find that x is negative 3. Going through this process, I was able to manipulate one equation so that we had an expression for the variable. So I took that and plugged it into the other equation so that I can actually solve for one of the unknowns. In this case, we found that x is equal to negative 3, which is half the battle. So we're almost done. Once we found that x is equal to negative 3, right, which is step 3, you solved, then step 4 would be, hey, plug it in. If we know that x is negative 3, plug it into one of the original equations so that we can find y. So notice here how I took the first equation, negative 4x plus y is equal to 6, and I said, okay, well, I know that x is negative 3. So I'm going to replace x with negative 3 and go through the motions. Negative 4 times a negative 3 is a positive 12, so I have 12 plus y is equal to 6. Subtract 12 from both sides, and look what we just found. Y is equal to negative 6. Now, some of you may be thinking, well, you found that x is equal to negative 3. Why did you plug it into the first one, into the first equation in our system? Well, you don't have to. I'm going to write out negative 5x minus y is equal to 21. And what I'm actually going to do is I'm going to substitute x is equal to negative 3 here in our second equation, just so I can prove to you that it doesn't matter which equation you plug this into. So negative 5 times negative 3 minus y is equal to 21. Negative 5 times negative 3 is a positive 15 minus y equals 21. Subtract 15 from both sides. Negative y is equal to 6. And then, if negative y is equal to 6, we divide both sides by negative 1. And what do you know? We get that y is equal to negative 6. If you happen to check in both equations and you get the exact same value, this serves as your check, which is pretty cool. This serves as the check for your system. If when you plug in your x, you get the exact same value from both equations, you know you did it correctly. So of course, we say that our solution to this consistent system, right, because they have one point of intersection, is the ordered pair negative 3, negative 6. And notice how we write it. We have to write it as an ordered pair, negative 3, negative 6. And we already had the discussion as to why. Excellent. Let's look at this in action. Number 1. 3x minus 2y is equal to 5, and we have x plus 10y is equal to 7. So again, strategy, right? We have to think about which equation should I manipulate and which variable should I get alone. So because this is your first time trying this on your own, I'm going to walk you through this. If I looked at each of these variables, 3x, negative 2y, 1x, 10y, I recognize right off the bat that it's going to be really easy for me to get x alone in my second equation. So I'm going to prove that to you. So if we write x plus 10y is equal to 7, we could say, well, I can easily get x alone by subtracting 10y. So let's do that. If I subtract 10y, I now have x is equal to, and again, negative 10y plus 7. We always like writing in descending order, so why not continue that process? So now we see that x is negative 10y plus 7. I just manipulated the second equation, which means I need to take this information and plug it into the first equation. So what I'd like us to do is I'd like us to circle the expression. Negative 10y plus 7. X is that negative 10y plus 7. I'm going to rewrite my first equation, the one that I did not manipulate, and I'm going to note that x is negative 10y plus 7. So x is negative 10y plus 7. That means we're going to substitute x for negative 10y plus 7. Oftentimes, I'm a very visual person, so oftentimes I'll circle, I'll draw arrows, whatever it takes. If that's your style, please join me, okay? It'll make it clear what you actually did. So we are going to make this substitution, right? Which is why it's called the substitution method. So we have 3 parentheses in place of x. Remember, x goes away because x is negative 10y plus 7. So we're going to replace x with this expression. So there's 3x minus 2y is equal to 5. Not bad, right? You make a direct substitution. Now all we have to do is do the math. We're now back in unit 2 where we're like, oh, I know how to solve this. All I have to do is distribute, right? So we have a negative 30y plus 21 minus 2y is equal to 5. As always, we clean up like terms first. So negative 30y and a negative 2y gives us a negative 32y plus 21 is equal to 5. We're trying to solve for y, so we want to subtract 21. That gives me negative 32y is equal to negative 16. Right? And if you want, you can always double check that. And of course, divide by negative 32. Let's cancel our coefficients. Negative 32 divided by negative 32 is 1. 1 times y is y. And then notice here we have a negative divided by a negative. The first thing I'm going to do is I'm going to clean this up. So that gives us a positive. 16 divided by 32, you probably punched it in and said it gives you 0.5, which is true, but I actually would like you to express your answer as a fraction, and we know that 0.5 is the same as 1/2, okay? Notice that we can divide both of these numbers by 16, which makes this fraction reduce to a 1/2. Okay, again, remember, this is half the battle. So we're looking for a solution here. And the solution is always of the form x, y. So it's kind of a reminder that that's what we're looking for. We are looking for an x and a y. We only have a y right now. So what we're going to do is we're going to take this y is equal to 1/2 and we're going to plug it into the original equations. I'm actually going to plug them into both of these just so that you can see how we do this check by plugging in. So we have 3x minus 2y, but y is 1/2 is equal to 5. And we have x plus 10y, but y is equal to 1/2 is equal to 7. Okay, so we're substituting the y is equal to 1/2 into both of the original equations. In all reality, you don't have to do this, but if you want to make sure that you're doing this correctly, you might as well, to make sure that you're getting consistent answers. So we have 3x minus, and then 2 times 1/2, or 1/2 of 2 is 1, right? So minus 1 is equal to 5, and we're just going to solve this first equation. We add 1, we get 3x is equal to 6, divide by 3, and we get that x is 2. Let's try it again. X plus, and then 1/2 of 10, or 10 times 1/2, again, 1/2 of 10 is 5. If we subtract 5 from both sides, we get that x is equal to 2. Awesome. So just like that, we can say that the solution is the ordered pair 2, 1/2. This is a consistent system. We can make a note of that. We know it's consistent because there's one solution, which is 2, 1/2. All right. Take a look at number 2. For number 2, we have 2x plus 3y is equal to 9. And then we're gifted y is equal to negative 3x minus 4. So I'm going to rewrite y is equal to negative 3x minus 4 because y is already by itself. That takes care of step number 1. Step number 1 was isolate one of the variables. Well, the beauty about this particular system is it was done for us. So I'm going to circle that negative 3x minus 4. We're going to take this expression and we're going to plug it into the other equation. You can't just plug it into itself. That's not a system, right? You have different pieces to a system. They must work together. So I'm going to rewrite 2x plus 3y is equal to 9. Y is negative 3x minus 4. Y is negative 3x minus 4. So I'm going to take this expression and replace y with it, okay? Or in other words, we're going to make that substitution. Okay, so we have 2x plus 3 parentheses because we're replacing y with negative 3x minus 4 is equal to 9. And now we just have to do the math. That's a beautiful part. Once you've taken care of this first step and you make that substitution, now it's all about just solving. Distribute to drop parentheses, combine like terms. We have negative 7x minus 12 is equal to 9. We're going to add the 12 to both sides. When we add the 12, we get negative 7x is equal to 21, right? So far, so good. Divide by negative 7. And we find that x is equal to negative 3. Cool. Very cool. So again, what we can do is take both equations, 2x plus 3y equals 9, and y is equal to negative 3x minus 4, and wherever we see an x, let's replace it with a negative 3 and see what happens. So 2 times negative 3 plus 3y is equal to 9. And we have y is equal to negative 3 times negative 3 minus 4. We're just making the substitution for the value that we found. If both of these equations give us the same answer, we know that we've solved this correctly and we made no mistakes. So for our first equation, we have negative 6 plus 3y is equal to 9. Add the 6 to both sides. That leaves us with 3y is equal to 15. Divide both sides by 3. And we get y is 5. Cool. Let's verify that the second equation gives us the same. So y is equal to negative 3 times negative 3 is a positive 9. And then 9 minus 4 is 5. Perfect. I love this. This is a great strategy to get into. So we'll write our solution as an ordered pair, always, x then y, so negative 3, 5. We know this system is consistent, so I'm going to make a little note that this is a consistent system. And we're done. That is just the start of substitution. Practice this method in Lumen because it follows the same concept. Isolate one of the variables, take that expression, plug it into the other equation, solve for that variable, and then take that solution, which is one of the coordinates, and plug it into both equations. You should. If you plug it into both equations and you solve and you get the same answer, then you know you did it correctly, and you feel confident about moving forward. So that would be my recommendation. Try that out, see how it goes. I hope that this made sense with this idea of substitution. I have the steps written out just so that you could reread this and make sense of it. And as always, watch the video again and again if you need to until it becomes perfect. All right? On that note, wonderful job today. Excellent, excellent work. And I look forward to seeing you all tomorrow. Enjoy the rest of your day. Bye.